Welcome to this course on stochastic modeling. In this lecture, we will look at some of the properties of exponential distribution. This will be in continuation with the last lecture. In this lecture, we will concentrate especially on the order statistics of a collection of exponentially distributed random variable. Let us look at a collection of random variables which are all exponentially distributed. Let x1, x2, x3 and so on are exponentially distributed random variables, each having its own parameter. Call it as lambda I. That is, xi is expo with parameter lambda I. If we have a collection of random variables and if you take a realization of these random variables and then look at the order the random variables realization or values in ascending order or descending order and consider the value those ordered values will be, they are what basically defines the order statistics. So if you take a collection of random variables and then consider what would be the minimum value of the realization of these random variables, and that would depend upon all the random variables, and that is what we call as the first order statistic. So the first order statistics is the minimum of n samples of a given random variable x, denoted as x within bracket 1. This is the convention that we normally follow to denote the random variables, which denote the order statistics. So it is just given by the minimum of x1, x2 to xn. On the other hand, if you look at the second minimum, that is, there is only one other realization which is minimum than this value, then that is called as the second minimum. Then the third minimum, fourth minimum, in this way we can discuss. And then you will have the nth minimum, which is nothing but the maximum among all these random variables. So if you arrange the realizations of the n random variables in increasing order, then the minimum is called as the first order statistics, and the maximum is called as the nth order statistics, and then the order in between are denoted as respectively by their position in their in the list of ordering. The ith order statistics will be the ith minimum in the ordering. So especially we will just look at how the first order statistics of a collection of exponentially distributed random variable will be. Again, the minimum itself will be a random variable. It will have a probability density function and so on, and that is what we would like to find. So to give a practical example where this order statistics will play a role is that, let us assume that we procure 100 bulbs, light bulbs, and we fix it in the office at the same time, and we assume that these bulbs have got a lifetime which need not all be same, but we model it as exponentially distributed random variable with different parameters. So lambda I is the parameter for the exponential parameter for the ith bulb and so on, which means that the lifetime of the ith bulb, which we denote it as xi, it will be given by lambda I e power of minus lambda I small x for x greater than or equal to 0. So having fixed it, we would be interested in the time at which the first bulb which will happen to fail among the 100 bulb being fixed. That time will obviously be the minimum of the realizations of the lifetime taken by the 100 bulbs. So this is the time at which the first replacement need to be done. So that is why we would be interested in this quantity. So we would be interested is the PDF and then CDF of the time to find the replacement that is to be needed for the first time. So in these such problems, it is better or easier to work with the CDF. So CDF of the lifetime of the bulb given by fxi of t for the ith bulb is 1 minus e power of minus lambda it, and obviously the CCDF given by probability that xi is greater than t is given by e power of minus lambda it. So we are interested in the minimum of these random variables. We will call it as, we will denote it as x, and this random variable denoted as x, which is the minimum of x1, x2 to xn, is what we are interested in, and its CCDF is by definition probability that x is greater than t is equivalent to probability that the minimum of x1 to xn being greater than t, because x by definition is minimum of x1 to xn. If you look at this statement, the minimum of the n realizations of the n random variables had to be greater than t, which means that each and every realization x1, x2, x3 and so on, all of them have to be greater than t. So we can write it as it boils down to n conditions, all of them have to be satisfied. That is probability that x1 greater than t, x2 greater than t to xn greater than t, and these are all conditions which are to be met, and they are independent of each other because the random variables are independent of each other. So the probability of intersection of many random variables, many events, can be written as product of their probabilities. So it is equivalent to probability of x1 greater than t, x2 greater than t and so on, and each one of them is nothing but the CCDF of the respective random variable. Therefore it is given by e power of minus lambda it, lambda 1t, lambda 2t and so on. We can in turn write it as e power of minus lambda 1 plus lambda 2 to lambda n to t. So this would be the CCDF of x, which is the minimum of x1 to xn. So that is, if you denote CDF as fx of t, it is 1 minus fx of t. So we therefore get fx of t is 1 minus e power of minus summation of lambda I varying from 1 to n into t. So we find that the minimum is again exponentially distributed, and its parameter is the sum of the parameter of all the comprising random variable, and its expected value for the first replacement to be done is 1 divided by the sum of the lambdas. Now let's consider another case where x1 and x2 are two random variables with the respective parameter lambda 1 and lambda 2. We are interested in the case, the event that the first and let them represents the lifetime of two components. We would like to find the probability that the first component fails before the second component. That is, x1 representing the lifetime of the first component is less than x2. So probability that x2 is greater than x1 is what we are interested in. So these are two random variables. How to find the probability of this kind? That can be done by conditioning x1 taking a particular value, and then unconditioning by weighing it with the probability density function and integrating it over the entire domain of x1. That is integral 0 to infinity probability that x2 greater than x1 given x1 is equal to a value t into fx1 of t dt. And this is nothing but in place of x1 you have to put t, because this is just the condition is x1 should be equal to t. So in place of x1 if you put t, you just simply get property that x2 greater than t multiplied by fx1 of t dt. And you know that this is CCDF of x2, which is e power of minus lambda 2t, and the next one is the PDF of x1, which is lambda 1 e power of minus lambda 1t into dt. So simply we can find it as lambda 1 into integral 0 to infinity e power of minus lambda 1 plus lambda 2t dt, which on integration will give you 1 over lambda 1 plus lambda 2. So we get the resultant property as lambda 1 by lambda 1 plus lambda 2. We can also arrive at the same value by looking at the mean value of x1 and x2, which are 1 over lambda 1 and 1 over lambda 2, and probability that x1 is less than x2 is that you find the ratio of the lifetime of x2 to the combined lifetime of x1 and x2. So the ratio of how much x2 is less than in comparison with x1 is what we are interested in. So that again, using that we can find the value as lambda 1 plus lambda 1 plus lambda 2. Then before we get into the sum of exponential random variables and talk about a collection of random variables which are all identical or non-identical and so on, we will again draw a analogy or the close connection between the exponential random variable and the geometric random variable. We already saw that in the case of continuous valued random variable, it is only the exponential random variable which has got the memoryless property. And in the case of a discrete valued random variable, it is only the geometric random variable which has the memoryless property. So we would suspect that they have to have a close connection. Indeed, that can be found out as follows. Suppose x is a exponential random variable. Let us look at a random variable which is mod of this a seal of x. What is it? It is the smallest integer greater than or equal to x. So if you consider this random variable, this would be a discrete valued random variable because x is continuous valued. On taking this seal, it becomes discrete valued. It will take values 1, 2, 3, 4 and so on. And therefore, we can find out its PMF. And that is what we would first find out and look at whether it takes a form which is known to us already. So what we are interested is in probability that x is greater than or equal to k is what we will find out. So that is probability that the seal of x is, this is seal of x is equal to k. Okay. So that will happen that from fx of k, you have to subtract fx of k minus 1. So whenever the x takes any value between just above k minus 1 all the way up to k, then seal of x will be equal to k. So that range, if you want to find out, you have to subtract the corresponding CDF. So fx of k is probability that x is less than or equal to k. So this has to be a seal, whereas this is the normal x. And minus fx x less than or equal to k minus 1. Substituting the formula for the CCDF of evaluated at k and k minus 1, here k is an integer. It is 1 minus e power of minus lambda k minus 1 minus e power of minus lambda k minus 1. That minus and minus becomes plus here. And then we can do some algebraic simplification. So what it leads is, this becomes, this 1 gets cancelled you will have e power of minus lambda into k minus 1 can be taken out as a common factor in this one. And then here you can have this will be 1, this will be e power of minus lambda k. You can see that if you multiply these two, e power of minus lambda and e power of plus lambda gets cancelled to get e power of minus lambda k, this factor with a minus sign, whereas this factor is the multiplication of this with 1. So if you look at carefully this one, then if you call this factor as p, and this factor will be nothing but 1 minus p power k minus 1. Okay. So from that, because 1 minus this is e power of minus lambda power k minus 1, so this is 1 minus p power k minus 1. So we can write this as probability that ceil x is equal to k is 1 minus p power k minus 1 into p, where p is simply given by this. So what we find is the ceil x has a PMF of this form, and we know that this is the PMF of a geometric random variable with a probability of success equal to p. Therefore we find that the ceil of x, where x is exponentially distributed random variable, is always a geometric random variable with parameter given by this. So that establishes a close connection between the exponential random variable and the geometric random variable. Then we will look at sum of n exponential random variables, all of them being identical. So it will turn out to be what is called as a gamma random variable, and the corresponding distribution is called as the gamma distribution. So let x1, x2 to xn be NIID. This is very important. Independent, identically distributed random variable. Because they are identical, they have the same parameter. We will call it as lambda. So xi is exponential with parameter lambda, and this is true for all i's. Then we are interested in the sum of these n random variables. So that is, we will define x equal to x1 plus x2 to xn. Then we are interested in the nature of the, again x is a random variable, so we are interested in finding the distribution of x. Again, what is the common sense or scenario which will lead to these kind of gamma random variable? One, suppose in the problem which we discussed earlier, we have 100 bulbs. Let us assume the lifetime of all these bulbs have got the same distribution and the parameter being lambda. We have to use only one bulb in our house. Then we take one from the packet of the bulbs from the lot, use it. The moment it goes away, get fused, we replace it by another new bulb, and so on until we run out of all the bulbs in the box of 100 bulbs. Then the total time duration for which we can use the bulbs from this whole box is that it is the sum of the lifetimes of 100 bulbs. Okay, it will have different distributions, the realizations, and every time we carry out this experimentation, but the sum will be a continuous valued random variable, and whose distribution is nothing but the sum of n exponential identically distributed random variable. Of course, we assume that the random variables are independent, because the failure or the time at which one bulb gets fused is not going to influence the lifetime of the next bulb being put into use. Well, now x is the sum of x1 plus x2 to xn, and its distribution we will call it as gamma distribution, and it can be shown that its distribution will take this form. Fx of t is equal to lambda e power of minus lambda t power n minus 1 by n minus 1 factorial. There can be many ways in which this can be shown to be true. What we will do is we will show it through induction. First we will take this as it is to be given, and then through induction we will prove that this is indeed true. So how do we go about doing it? We will first verify whether this expression is true for the case of n equal to 1. That is, there is only one random variable x1 and x equal to x1, and this formula which gives the sum whether it is true. So for the case of n equal to 1, the PDF is given by lambda e power of minus lambda t, and here you will see 1 minus 1 0, here also 0 factorial. So this will be just 1. So you get the PDF being lambda e power of minus lambda 2, and we know that is just the density function of the exponential random variable, that is x1. So it is trivially true for the case of n equal to 1. Suppose this is true for n minus 1, that is, if x equal to x1 plus x2 to xn minus 1, if this formula holds good, then we will check whether it will hold good for n. In the case of sum of n minus 1 random variables, x1 plus x2 to x minus 1, this formula yields fx of t is equal to, we will call this sum as s. Fs of t is equal to lambda e power of minus lambda t, sorry. Okay, and here the number is n minus 1, so we will get lambda t power n minus 1 minus 1, that is n minus 2. Similarly here also we have got n minus 2 factor. So this would be the formula for the density function of sum of n minus 1 IID expo random variables with a common parameter lambda. Now if you talk about sum of n random variables, which we denote it as x, it will be x1 plus x2 to xn minus 1 plus xn. If you take from x1 to n minus 1, that is what we denoted it as s. Therefore this x is nothing but s plus xn, and we know the density function in both of them. Xn is just an exponentially distributed random variable whose density function is known to us, and yes, we assume it to take this form. If this assumption is true, then x is nothing but the sum of two independent random variables. See, xn is independent of all the other random variables x1, x2 to xn, so it is xn is independent of s. So fx of t is f of s plus x of t, and therefore we can get this through the formula of convolution of two density functions. So it is given by integral from s equal to small s equal to 0 to t fs of s into fxn of t minus s ds. Okay, so this is the convolution formula. Let us plug in the expressions for the density function in this integral. Integral 0 to t, for the case of fs of s, we will put this formula. So where in place of t we put small s. So lambda e power of lambda s power n minus 2 by n minus 2 factorial into, for xn we will put lambda e power of minus lambda t. Lambda e power of minus lambda into evaluated at t minus s. So that is what we will put. We will take the common things outside the integral, that is lambda e power of minus lambda t. This lambda e power of minus lambda t can be taken out, and then lambda power n minus 2 by n minus 2 factorial also we will take it out. So what will remain inside? The s factor will be inside because it is an integral is over s. That is e power of minus lambda s will be there plus lambda. Here we will have, will be there, and then s power n minus 2 will be there. Here we will have e power of minus lambda s. Here we will have e power of plus lambda s power n minus 2 into ds. These two factors cancel each other. So we only have s power n minus 2 into ds. On integration, this will give s power n minus 1 by n minus 1 evaluated between 0 to t. On substituting t, we will get t power n minus 1 by n minus 1. After multiplication, this will give you lambda e power of minus 2 lambda t. We can club lambda and t together as single factor with a common power of n minus 1, and at the denominator, these two factors we can write it as n minus 1 factorial. And then we see that this is our original assertion that the sum of n exponential IID random variables is gamma with this form, with PDF of this form. So by induction we have shown that this claim of the distribution of sum of IID random variables or gamma distribution is right. Then we will look at the case where we have random variables which are all exponentially distributed but not necessarily having identical distribution. But still we will assume they are all independent of each other. So we have a sum of n independent, non-identically, but all exponentially distributed random variable. Again, we can easily think of an experiment that you have a case where you have light bulbs whose lifetime is varying in nature and they are put into use. One more interesting example would be that they consider a relay in which there are 4 runners. They have to pass the stick to the other person until the relay gets completed. The time taken for each one of them, okay, if it is exponentially distributed, then each one will, the time taken will be different, and it will be non-identical depending upon the capability of the person. So it will be a sum of non-identically but independently distributed random variable. In case if it is exponential, then that is what we are interested in, and we will give a name for it. We will call that such random variables are hypo-exponential random variables, and the corresponding distribution as hypo-exponential distribution. So let us have n random variables x1, x2 to xn, xi being exponentially distributed with a parameter lambda I. So consider their sum x, which is x1 plus x2 to xn. First, we will show it for the case of sum of 2 independent non-identical exponentially distributed random variable. That is for the case of n equal to 2, which is the first step we will do, and then we will try to generalize. For the case of n equal to 2, x is given by x1 plus x2. x1 is expo with parameter lambda 1, x2 is expo with a parameter lambda 2. So fx of t is integral s to 2. Again, by convolution we will find out the distribution of x. S equal to 0 to t, fx1 of s, fx2 of t minus s ds. So substituting the PDF of x1 and x2, for x1 it is lambda 1 e power of minus lambda 1 s. For x2 it is lambda e power of minus lambda 2 evaluated at t minus s into ds. So take out lambda 1, lambda 2 outside the integral, and even e power of minus lambda 2, which is independent of the integration variable. What we are left out is integral 0 to t e power of minus lambda 1 minus lambda 2 into s ds. So that on integration will give you this e power of minus lambda 1 minus lambda 2 to s divided by minus of lambda 1 plus lambda 2 evaluated between 0 to t. So substitute t and subtract it from on substituting 0. That on substitution will give you just 1. So this is what you would get. Now if you multiply e power of minus lambda 2 with this one, okay, you will get this form. You can easily see. So if you multiply it by 1, we will get lambda 1, okay, lambda 2 e power of minus lambda 1 t. So this is what you would get, okay. And then see here in this, for 1 also there will be this term. Yeah, that is very important. For 1 also it will be there. It was not mentioned here. So this will be a common factor. Okay, this minus 1 on multiplying, we have changed the sign, okay. That we have retained it here, okay. But later on if you change it, it will be lambda 2 minus lambda 1. And here if you multiply it, and then the e power of minus lambda 2 t will get cancelled with e power of plus lambda 2 t, okay. And what we will have is e power of minus lambda 1 t, okay. That is what comes here. So this is the formula that we get. So how do we try to write it in a systematic manner if you generalize this to n variable? It looks like for every x that is present in the sum, there will be one such term, number 1. That is one k thing. So it will have a factor which is given in the bracket plus lambda 2 e power of minus lambda 2 for the case of the one which x2 contributes, lambda 1 e power of minus lambda 1 t for the case x1 contributes, and so on. So that is one thing that is always there. So for each xi will contribute some coefficient which will denote it as ci times lambda I e power of minus lambda I t. This coefficient ci in this case has the form lambda 1 by lambda 1 minus lambda 2. So for the case of x2, we will have lambda 2 here and lambda 1 here. If we had 3 random variables, 1, 2, 3, we will have one factor for each of the x's other than 2, okay. So in general we can write ci as there will be n minus 1 factor, okay, such that is j is equal to 1 to n, j not equal to I. For the coefficient for the ith one will be such that it is lambda j by lambda j minus lambda I, okay. So for look for x2, we have got x1 lambda 1 by lambda 1 minus lambda 2. If there were 3, then there will be lambda 3 by lambda 3 minus lambda 2. All will be present multiplied by lambda 2 e power minus lambda 2. So that is how we have got this one. So the distribution of x is called as the hypo-exponential distribution. Then we have another variation that we can think of. First we will motivate it using an example wherein you have a factory which sources component from different manufacturers, and all these components which come from different manufacturers are being put together in the inventory, and whenever needed you randomly pick one of the component and use it. Then the lifetime of each of the components, we know it is exponentially distributed, but the component that comes from factory 1 has one particular parameter as compared to the component given from the factory 2, because of the variation in the manufacturing process. Some will be more reliable, some will be less reliable. The lambda I from the ith factory fix the nature of the component produced by the ith factory. And then you also consider the case where 20% of the items are sourced from factory 1, 30% from factory 2, and 40% from factory 3, and so on. If that is the case, and if these items are being thoroughly mixed and put in a bin, and if you take out one randomly, we can see that that item may come from factory 1 with a probability 0.2, from 3 with 0.3, and so on. So now what will be the lifetime of this randomly picked component? Only thing that we know is it is exponentially distributed. If it comes from the ith factory, it will have a lifetime xi with a parameter lambda I. And probability of that being happening is pi, which is the pi is the probability that we would source a component from the ith factory. So we have got probability that a randomly picked component will be from the ith type. So sigma I varying from 1 to n pi is equal to 1. Now we will also introduce a random variable t that specifies the factory from which the component is procured. We will give a number for each of the factory as 1, 2, 3, and n. If t is equal to 1, it means the component came from factory 1. T equal to 2 means it came from factory 2, and so on. And let's assume that we know the proportion of the components being sourced from each factory, and therefore we know probability that t is equal to I, which we will denote it as PA. And naturally sigma I varying from 1 to n, PI is equal to 1. So the lifetime of the component randomly picked from this lot and put to use, okay, is what we are interested in. If it were from factory Fi, then it is xi with parameter lambda I. So how do we find it? So we compute this. First we will consider the CCDF of the x, which is the lifetime of a randomly picked component, to be greater than t. If you know that the item that is being picked is from the ith factory, then we know what this one is. This is nothing but the CCDF of xi. So we will put that condition. Given that t is equal to I, that is the item comes from the ith factory, probability that x greater than t is what, supposing we use that and assume that it is known, indeed that is known of course, then how do we uncondition it? Then we have to multiply it by probability that t equal to I and then sum it over all. That given that the component comes from the ith factory, then probability that x greater than t is being found out using this. So in this case we know that if t is equal to I, it came from the ith factory, and in which case x becomes xi. We can directly put it, probability that xi is greater than t into probability that t is equal to I. And we know the CCDF of xi, which is e power of minus lambda it, and probability that t is equal to I is Pa. So we have immediately found out the CCDF of x. If you want the CDF of x, it is 1 minus this, 1 minus probability that x greater than t, which is 1 minus sigma I varying from 1 to n Pi e power of minus lambda it. If you want the probability density function, again then it becomes easier. On differentiating with respect to t, you get that this goes away, and then e power of minus lambda it will give you minus lambda I into this. The minus and minus goes away. You simply have Pi lambda I e power of minus lambda it, that being summed from 1 to n. So this random variable is called as the hyper exponential random variable. The distribution is called as the hyper exponential distribution, and more often it is called using the abbreviation HED distribution. Then we will quickly go through one example. That you have a bank where there are to just check whether we can put into use the formulas that we have seen. There are two counters and both the counters are empty. One customer arrives, but these counters are being served by servers. They have different service rate. Their service time is exponentially distributed, and the parameters is lambda 1 and lambda 2. Customer 1 enters the bank and finds that both the counters are empty, and therefore the customer 1 goes to the teller 1, whose service rate is lambda 1. Yes, a time of S time unit passes, and then customer 2 enters. When the customer 2 enters, customer 2 finds that the server 1 is busy servicing customer 1, and therefore the customer 2 has no choice. Customer 2 goes to the server 2 and start the service. Okay. Now, given this situation, we would like to know what is the probability that customer 2 leaves the bank before customer 1. Note that customer 2 came late only after a time unit of S has expired after the customer 1 starts. What is the probability that customer 2 leaves? That is the question. You might think that it depends upon the rate of service of server 1 and server 2, of course. It might also depend upon S, the time that is being spent by customer 1. But the thing is, it is given that when customer 2 enters, customer 1 is still under service. So now the question is, we have to compare the remaining time the customer 1 spends with the server 1 with the time, full service time that customer 2 spends with the server 2. But because of the memoryless property, okay, the remaining service time of x1, which we will call it as x1 dash, has the same distribution as x1, which is lambda, which is exponential with the parameter lambda 1, and therefore probability that x2 is less than x1 dash, because x1 dash has the same distribution as x1. We are asking the question, what is the probability that x2 is less than x1 dash, where x2 is exponential with parameter lambda 1 and x1 dash also is exponential with the parameter lambda 2. Okay, so x2 with lambda 2, x1 dash as well as x1 as parameter lambda 1. So this we have already derived to have this formula. So with this example, we will stop our discussions on the properties of exponential random variable. We will take up the Poisson stochastic process in the next lecture. Thank you.